Hello guys. Today we will continue our Dark Matter Series 4. We will talk about sterile neutrino, the hypothetical particle related to dark matter. Sterile neutrinos, or inert neutrinos, are hypothetical particles that interact only via gravity and do not interact via any of the fundamental interactions of the standard model. The term sterile neutrino is used to distinguish them from the known active neutrinos in the standard model, which are charged under the weak interaction. This term usually refers to neutrinos with right-handed chirality, see right-handed neutrino, which may be added to the standard model. Occasionally it is used in a more general sense for any neutral fermion. The existence of right-handed neutrinos is theoretically well motivated, as all other known fermions have been observed with left and right chirality, and they can explain the observed active neutrino masses in a natural way. The mass of the right-handed neutrinos themselves is unknown and could have any value between 1015 gigaelectronvolts and less than 1 eV. The number of sterile neutrino types is unknown. This is in contrast to the number of active neutrino types, which has to equal that of charged leptons and quark generations to ensure the anomaly freedom of the electroweak interaction. The search for sterile neutrinos is an active area of particle physics. If they exist and their mass is smaller than the energies of particles in the experiment, they can be produced in the laboratory, either by mixing between active and sterile neutrinos or in high-energy particle collisions. If they are heavier, the only directly observable consequence of their existence would be the observed active neutrino masses. They may, however, be responsible for a number of unexplained phenomena in physical cosmology and astrophysics, including dark matter, baryogenesis or dark radiation. Sterile neutrinos may be neutral heavy leptons, NHLs, also called heavy neutral leptons, HNLs. Experimental results show that all produced and observed neutrinos have left-handed helicities, spins antiparallel to momenta, and all neutrinos have right-handed helicities, within the margin of error. In the massless limit, it means that only one of two possible chiralities is observed for either particle. These are the only helicities, and chiralities, included in the standard model of particle interactions. These particles would belong to a singlet representation with respect to the strong interaction and the weak interaction, having zero electric charge, zero weak hypercharge, zero weak isospin, and, as with the other leptons, no color, although they do have a BL of -1. If the standard model is embedded in a hypothetical SO10 grand unified theory, they can be assigned an X charge of -5. The left-handed antineutrino has a BL of 1 and an X charge of +5. Due to the lack of charge, sterile neutrinos would not interact electromagnetically, weakly, or strongly, making them extremely difficult to detect. In experiments involving energies larger than their mass, they would participate in all processes in which ordinary neutrinos take part, but with a quantum mechanical probability that is suppressed by the small mixing angle. That makes it possible to produce them in experiments if they are light enough. They would also interact gravitationally due to their mass, however, and if they are heavy enough, they could explain cold dark matter or warm dark matter. Check my video about them. To talk about its mass, all particles are initially massless under the standard model, since there are no Dirac mass terms in the standard model's Lagrangian. The only mass terms are generated by the Higgs mechanism, which produces non-zero Yukawa couplings between the left-handed components of fermions, the Higgs field, and their right-handed components. Such is the case for charged leptons, like the electron, but within the standard model, the right-handed neutrino does not exist, so even with a Yukawa coupling neutrinos remain massless. In other words, there are no mass terms for neutrinos under the standard model. The model only contains a left-handed neutrino and its antiparticle, a right-handed antineutrino, for each generation, produced in weak eigenstates during weak interactions. See neutrino masses in the standard model for a detailed explanation. I will stop here for now. But tell me, what are the hypothetical particle you want me to talk about next? See you next time.